Hello everyone. I hope you are all doing good. So today's our topic is electrostatic potential and capacitance, NCERT Section 2.10 to 2.11. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So the topics that we are going to cover today is dielectrics and polarization and capacitor and capacitance. Objective: to study the behavior of conductor and dielectric in external electric field. So dielectrics are non-conducting substances without charge carrier, unlike conductors. So far we have discussed in our previous lecture that conductors, that behavior of conductors in external electric field. But now we are going to discuss about behavior of dielectric in external electric field. So what are dielectrics? Dielectrics are non-conducting substances without charge carrier. So in conductors, most of the conductors are metals. So conductors have free charges, mobile charges. In the case of metals, that mobile charges are electrons. And in the case of electrolytic solutions, that charge carriers are ions, positive and negative ions. So dielectrics are non-conducting without charge carrier. So in dielectrics, there are no free charges. So they are without charge carriers, unlike conductors. When a conductor is placed in an external electric field, free charge carriers move to oppose the external field. That we already discussed that what happened inside the conductor when there is external field applied across the conductor. So the free charges that are present in the conductors adjust or distribute themselves according to the external field such that the electrostatic field inside the conductor becomes zero. So the free charges that are present in the conductor, they will distribute or arrange themselves in such a way that the net external field inside the conductor becomes zero because of the induced electric field that is produced by the charges, free charges after distribution, that is equal and opposite to the external field. So this is the phenomenon that was happening inside the conductor. So what was the phenomenon that will be happening inside the dielectric? However, in dielectrics, this free movement isn't possible. So in dielectric are mostly non-conducting and non-metals. So what happened in the dielectrics, the electrons are not free or loosely bound. They are very strongly bound by the nucleus. So they are not free to move inside the substance. So in dielectrics, free movement isn't possible because electrons are not free or any other ions are not free. So this is the diagrammatic example representation of the behavior of conductor and dielectric in the external electric field. So this is the external electric field E naught. So it is in this direction as shown. So the charges, the electrons or any other ions that are present in the conductor, whether it is metal or electrolytic solution, it depends on the type of substance, but there are free charges. So in the influence of external electric field, negative charges move in the opposite direction of electric field and accumulate on this side, and positive charges experience force in the same direction of electric field and accumulate on this surface, due to which induced electric field is generated inside the conductor, which is equal and opposite to the external electric field. So inside the conductor, this induced electric field cancel out the external electric field, due to which net electric field inside the conductor is 0. So external electric field plus induced electric field equal to 0 inside the conductor. Sum of these two electric field is 0 inside the conductor because they are equivalent in opposite direction. So this sigma free, what is this sigma free? This is the surface charge density due to free electrons, due to free ions or free charge carriers. So this is surface charge density due to free charge carriers that are present inside the conductor. Figure 2.20, difference in behavior of conductor and a dielectric in an external electric field. So what is the behavior of conductor? We are going to discuss again and summarize it. First one, conductor in external electric field. Free charge carriers move within the conductor. So there are free charge carriers inside the conductor. Charge distribution adjusts automatically. So charges on application of external electric field, they will adjust or distribute themselves automatically in such a way that they can produce an additional electric field that is equal and opposite to the external field. So they will adjust accordingly. So induced charges create an opposing field. So these charges that are induced on the surface due to the external electric field, that creates an opposing field inside the conductor, that is E induced. Eventually the two fields cancel each other. So these two fields, external and induced, cancel each other inside the conductor. So net electrostatic field becomes 0 inside the conductor. So net electrostatic field will become 0 inside the conductor. Now again the diagram, same diagram. And difference in behavior of conductor and a dielectric in an external electric field. Now dielectric response to external field. So what is the behavior of dielectric material inside the external electric field? So free movements of charges is not possible. It is already known that they are insulators. There are no free charges present. So free movements of charges is not possible in the dielectrics. External field induces dipole moments by stretching or reorienting the dielectric molecules. This term stretching and reorienting, this is in the detail in next slides. So I will explain there in detail. So I will give some a small idea of this. So what is this? This is the dielectric medium. So there are no free charges present. So what external field do to the molecules of dielectric? The molecules of dielectric, if the positive charges and negative charges inside the molecule is not distinguishable, means it is on the same place. So there is no dipole moment of the molecules. There is no net dipole moment of the molecules. So this external field will induce the dipole moment by stretching the molecule, by stretching the positive and negative charges in the opposite direction, and hence stretches the molecule. So by this thing, it will induce the dipole moment of the molecules in the dielectric. Or if there is permanent dipole moment already of the molecules of dielectric, then it will reorienting them. So if there is a permanent dipole moment of the molecules of the dielectric, it will arranged randomly in the absence of external electric field. So when we apply the external electric field, these dipole moments, these molecules that have permanent dipole moments tends to align along the external field. So hence net dipole moment comes into play. So external field induces dipole moments by stretching or reorienting the dielectric molecules. By this phenomenon, here negative charges induces, here positive charges induces. But this is not due to free charges like conductors? It is due to the reorientation or stretching of the dielectric molecules. So there is induced electric field due to these surface charges inside the dielectric. But now in the case of dielectric, this induced electric field has not equal magnitude to the external field. It is also shown in the form of arrow length. The arrow length of external electric field is more. The arrow length of induced electric field is small. This means this is a representation that induced field inside the dielectric is less than the external field. So it will not cancel out completely the external electric field. It will only reduce the external electric field. This is the major difference between the behavior of dielectric in external field or conductor in external field. Surface charges develop due to collective molecular dipole moment. So surface charges develop due to collective molecular dipole moment of all the molecules, not one molecule. So collective molecular dipole moments due to which surface charges develop. What is the mechanism? We will also see in detail in the next slides. Effect depends on dielectric nature. So which amount of surface charges will induce on the surface? It is entirely depending on dielectric nature. So what type of dielectric is there? It is a strong insulator, or it is somewhat conducting or somewhat insulating, not proper conducting or perfect insulator. It entirely depends on dielectric nature, that how much amount of charges are present on the surface of the dielectric when external field is applied. Again, same diagram, figure 2.20. Now, key differences between conductor and dielectric. What are the key differences? In conductor, opposing field completely cancels out the external field. So in conductor, what we have seen, that opposing field completely cancel out external field. But in dielectric, opposing field only reduces external field. It does not achieve complete cancellation. Why? Because the induced field is hasn't same magnitude as of external field. It has less magnitude than the external field. So it will not completely cancel the external field. It only reduces the external field. So now substances from which the dielectric is made is based on two classification. So molecules that are present in the dielectric, either they can be polar or non-polar. Non-polar molecules, centers of positive and negative charges coincide. So in non-polar molecules, centers of positive and negative charges coincide. Means the collective effect of positive charge in the molecule, and where this effect is present, the collective effect of negative charge should be there only. So the effect of both the positive and negative charges should coincide, so that the net dipole moment of the molecule will be 0. Okay, I will explain it with the help of electronegativity in the diagram. What are polar molecules? Center of positive charges. What is center? They are inferring here. Center of positive charge means the collective effect where the positive charge is, the collectively positive charge where is present inside the molecule. So collectively the effect of positive charge present in the molecule, and collectively negative charge, whole negative charge, the effect of negative charge is present at another point. So if the centers of positive charge and negative charges are separated, not on the same place, so there is a net dipole moment due to this. So that molecules are called polar molecules. An example, hydrochloric acid, HCl and water. So this is the diagrammatic representation. Now you have already studied electronegativity. Okay, so what is electronegativity? Tendency of an atom to attract the shared pair of electrons in the covalent bond. So like oxygen, fluorine, chlorine, nitrogen, they have high electronegativity. Halogens have high electronegativity. So the tendency of attract the shared pair of the electrons towards itself is the electronegativity. So non-polar molecules, here this is hydrogen, this is hydrogen, same element. So their electronegativity will be same. So they have shared 2 electrons here. So it will attract this shared pair towards itself. It will also attract with towards itself. So the effect get cancelled. So this shared pair will lie exactly in the mid of these 2 atoms. So what is the dipole moment now? The effective positive charge and effective negative charge will lie on the center. There is no charge separation, due to which the center of the positive and negative charges lie on the same point. So this is non-polar. There is no net dipole moment of this molecule. In the case of carbon dioxide, so its structure is linear. So you may have studied that oxygen is more electronegative than carbon. So here is the shared pair of electrons. So oxygen will attract it. So there is double bond. Okay, so these are shared pair. This is also shared pair. 2 pairs of electron. So oxygen will attract it, and here this side oxygen will attract it towards itself. So electrons get attracted towards this oxygen, electrons get attracted towards this oxygen. Now the oxygen will, these both atoms of oxygen get partial negative charge due to attraction of electron towards itself. They will get partial negative charge, and this carbon will get partial positive charge. So dipole moment, now dipole moment will have direction from this partial negative to partial positive. So it will have direction towards itself, toward this carbon atom, and here from partial negative to partial positive, this. But this dipole moment have direction equal and opposite, and the structure of this carbon dioxide is linear. So effect of these both dipole moments get cancelled. So net dipole moment of this molecule is 0 here. So it is non-polar molecule. Okay, now what is the polar molecule? HCl, hydrogen chlorine. Chlorine is more electronegative. So here is a shared pair of electrons. So this chlorine will attract this shared pair of electron towards itself and get partial negative charge, and this hydrogen will get partial positive charge. So dipole moment is from partial negative to partial positive. So dipole moment will be in this direction, net dipole moment. So these polar molecules, they have permanent dipole moment due to the difference of electronegativities. So these molecules will have permanent dipole moment. Now this is water molecule. Now this oxygen will have more electronegativity. It will attract the shared pair of this electron towards itself. Also this shared pair of electron towards itself. Now oxygen will get partial negative charge, and these both hydrogen will get partial positive charge. So dipole moment will have direction from partial negative to partial positive. Here also same. Okay, so what this dipole moment and this dipole moment, they are not equal, they are not in the opposite direction. They are equal but not in the opposite direction. So they will sum up and give some net dipole moment. So there is a permanent dipole moment of this molecule. So this molecule is polar molecule. I hope you understood the concept of polar and non-polar molecules. Here also the direction is shown. This direction of dipole moment is for this, and this is net dipole moment of this molecule. Understood? So these are non-polar and polar molecules, of which these are the two type of molecules of which the dielectric substances are made of. So figure some examples of polar and non-polar molecules. In an external field, non-polar molecules develop induced dipole moments when positive and negative charges are displaced oppositely. So non-polar molecules develop induced dipole moments. So they are non-polar. They don't have any charge separation. Their center of positive charges are present on the same point where center of negative charges are present. So when external electric field is applied, so what it will behave, how it will behave, the positive charges will experience force in the direction of electric field and the negative charges will experience the force in the opposite direction. So there is stretching. So that term stretching is related to that point. Okay, so positive charge will experience force in the direction of electric field and negative charges will experience force in the opposite direction. So there is a stretching of molecules due to which dipole moment induces. This is the case of non-polar. Now polar molecules, permanent dipole moments align with the field. So now we have seen that polar molecules have permanent dipole moment due to which, but they are randomly oriented in the absence of external field. Why they are randomly oriented? Due to thermal agitations. What is thermal agitations? Thermal agitation means due to temperature. Due to temperature, these dipole moment have randomness. They are aligned in any random direction so that the net dipole moment inside the dielectric is 0. So in the presence of, when we apply external electric field, these dipole moments that are oriented randomly due to thermal agitations will align with the field. So this is the diagrammatic representation. Here is the non-polar molecules. The center of positive charges coincides with the center of negative charge. When we apply the electric field in this direction, suppose, what will happen? Negative charges in the molecule will experience force in the direction opposite to the external field and positive charges will feel that force in the direction of electric field. So this molecule will stretch like this. So here partial positive charge appears, here partial negative charge appears. So dipole moment will be in direction this, from partial negative to partial positive. So dipole moment will have same direction as of electric field. Okay, so this is the stretching of molecules. Now in the case of polar molecules, these dipole moments from negative to positive, from negative to positive, from negative to positive, negative to positive. So these dipole moments will randomly oriented in any direction due to thermal agitation, due to temperature of the dielectric. So that the net dipole moment of whole substance is 0. So when we apply electric field, the positive charges in this molecule will experience force in the direction of electric field and negative charges will experience force in the opposite direction. So what will happen? These are also not perfectly aligned. So it will depend on the dielectric nature and other factors like temperature and etc. So due to temperature will produce thermal agitations, which is randomness due to temperature, and will restrict the complete alignment of these dipole moments. But if we are applying weak electric field, also this is a factor that it will not align perfectly, and it is also dependent on dielectric nature. So but they are, you can see they are nearly aligned. All the dipoles are nearly aligned in the direction of electric field except one, two. Okay, so they will tends to align in the direction of electric field. So here electric field is not 0. Figure 2.22. A dielectric develops a net dipole moment in an external field. A diagram is for non-polar molecules and B is for polar molecules. Now, dipole moment per unit volume is denoted by P, polarization vector. Dipole moment is net dipole moment of the whole substance. Per unit volume of the substance we have taken is denoted by P, that is polarization, or can be said polarization vector. For linear isotropic dielectrics, what are linear isotropic dielectrics? Linear isotropic dielectrics are those dielectrics that are in which the molecules stretch and the dipole moments, induced dipole moments, will align in the direction of electric field completely. All the molecules that have induced the dipole moment will align in the direction of electric field completely. These are called linear isotropic dielectrics. So this polarization vector is proportional to epsilon naught and external electric field. So this polarization vector is proportional to epsilon naught and external electric field, and this symbol, this is known as chi. So chi E is the constant of proportionality and is known as electric susceptibility, where chi E is the electric susceptibility of the dielectric medium. So what is electric susceptibility? Electric susceptibility is the measure of easiness, that how easy the dielectric get polarized. Means how easily dielectric get polarized, it is a measure of that thing. That if with a weak electric field we can polarize dielectric medium completely, then its electric susceptibility is more, we can say. If it is not getting polarized completely after application of large amount of electric field, then we can say its electric susceptibility is low. Okay, so electric susceptibility is the measure of how easy dielectric get polarized. When a rectangular dielectric slab is placed in a uniform external field E0, it causes uniform polarization. Okay, now we are taking one dielectric slab and placing it in the external field E0. It causes uniform polarization. Okay, it causes uniform polarization means almost all the molecules are aligning in the direction of, dipole moments are aligning in the direction of electric field. Each volume element delta V has a dipole moment P delta V. Now what is P? Polarization vector, dipole moment per unit volume. And multiplying, we are taking some volume element inside the dielectric, and the dipole moment of that volume element is net dipole moment per unit volume, that is polarization, into delta V of that element. While there is no net charge inside the dielectric, surface charge develop normal to the electric field. Only surface charges induces on the dielectric. Inside the volume there is no net charge. Why? Now we will discuss in next slide. So there is no net charge inside the dielectric. Surface charges develop, and these surface charges are normal to the electric field. Why normal? We have also discussed in the previous lecture that we have to attain static condition. We are dealing with static charges. If the electric field is not normal to these charges, there will be tangential component and it will result in movement of charges, which will produce current, and we don't want it in the electrostatics. So we only want static charges. So electric field is normal to the charges developed. Now it is represented in this diagram also. So this is the dielectric slab, and we are applying the electric field in this direction. Due to the application of external field, these electrons inside the negative charges inside the molecule will experience force in the opposite direction of electric field, and the positive charges present in the molecule will experience force in the direction of electric field, and this type of arrangement will form. These are the stretched molecules. So this type of arrangement will form, and now this positive charge of this molecule is close to this negative charge of other molecule. So it will cancel the effect of this charge. This positive charge will cancel the effect of this negative charge. This positive charge will cancel the effect of this negative charge. And this positive charge will cancel the effect of this negative charge. So inside the volume, this white portion, except this blue portion, this white portion, inside this white portion, all the charges are cancelling the nearby charge, neutralizing the nearby opposite charge. So this positive is neutralizing this charge, this positive is neutralizing this charge, and this positive is neutralizing this charge, due to which the net charge in the entire volume of the dielectric will result in zero net charge. So inside the dielectric there is no net charge. Now these surface charges, these negative, 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 and this positive, there is no positive charge present near this negative charge. There is no positive charge present near this negative positive charge. So they will remain as it is. They will not neutralize. So surface charge densities will appear because due to these surface charges. This is sigma p. What is sigma p? Surface charge density due to polarization of vector. Surface charge density due to polarization of vector. So this is sigma p. Okay. Okay. So these surface charge densities, sigma p and minus sigma p, these are surface charge density due to polarization. Now, this is the net dipole moment. All the dipoles are aligned in the direction of electric field. This is the net dipole moment. This is the polarization vector. Net dipole moment upon net volume of this. Okay, so this is the net polarization vector. Net dipole moment upon unit volume. Okay, so this is surface charge densities. Now, these surface charge densities, these charges appear due to bound charges. These charges are not free. In conductors, the charges that appear on the surface are free charges. In this case, these are not free charges. These are bound charges. And due to which large amount of charges are being cancelled inside the volume. So these charges are not as much large amount as in the conductor. So the induced field that is being produced due to these surface charges is less in amount than external field. So it is not equal to the external field. So it will only reduce the external field inside the dielectric, but not completely cancels it. Okay. A uniformly polarized dielectric amounts to be induced surface charges density, but no volume charge density. Polarized dielectric create two charged surface with induced surface charge density sigma p and minus sigma p. So polarized dielectric creates two charged surface. This negative charge surface, this positive charge surface with surface charge density minus sigma p plus sigma p. These charges oppose the external field, reducing the total field. They can only reduce the total field because these charges are not in the much amount, because most of the charges are being cancelled inside. These are only surface charges. So the electric field that is induced due to these charges is less in amount than this external electric field. So it will only reduce the external electric field inside a dielectric. These surface charges arise from bound charges, not from free charges. So this should be remembered. Now, next topic, to understand the capacitance, capacitor and its properties. A capacitor consists of two conductors separated by an insulator. So, what is capacitor? There are two conductors present and they are separated by any insulating material, or can be said dielectric medium. Okay, so capacitor, what is capacitor? Two conductors are there. It can be, conductors can be in the shape of sheet or can be in the shape of cylindrical shape or spherical shape, any shape of conductors. So these consist of two conductors separated by an insulator. The conductors have charges Q1 and Q2. One conductor will have charge Q1, other have Q2. And potential, one conductor have potential V1 and another have V2. So this is capacitor. A capacitor consists of two conductors separated by insulator. Charges on two conductors are different, and also potentials on both the conductors is different. Now, but in practice, in which we are going to discuss in the whole chapter, uh, the charges on the conductors will be taken as plus Q and minus Q. On the one conductor, it will be plus Q. On the other conductor, it will be minus Q. This is the practical term. Okay, this Q1 is plus Q, this Q2 is minus Q. With potential difference, V1 minus V2. Potential will be different. One will have high potential, one will be at higher potential, other will be at lower potential. So the potential difference between them is V1 minus V2. And the charges on one conductor is plus Q and another conductor is minus Q. A single conductor can serve as capacitor. A single conductor can be used as capacitor, but there is an assumption that the other conductor is at infinity, so that it will not affect the single conductor. So single conductor also can be considered as capacitor with the assumption that second is at infinity. So by definition, it is consist of two conductors, but we can also take single conductor as capacitor, but we have to assume that another conductor is at infinity. The conductors are charged by connecting to battery terminals. While Q represents the capacitor charge on one conductor, the total charge is 0. So conductors are charged with the help of battery. One positive terminal is connected with one conductor, and the negative terminal is connected with another terminal. Negative terminal is connected with another conductor. So while one conductor will have positive potential, one conductor will have negative potential. So potential difference between them is V1 minus V2, and charge on both the conductors will be same. One will be at positive charge, one will be at negative charge. So the conductor which is connected to positive terminal will be having positive charge, and the conductor which is connected to the negative terminal will be having negative charge. So while Q represent the conductor charge, now in the upcoming chapter, in this chapter only, we will now, when we are going to discuss about the charge on the capacitor, we will represent it with Q, charge on one conductor, specifically on the conductor that has positive charge. We will say that the charge on the conductor is Q. We will not say that charge on one conductor is plus Q and minus Q. We'll consider that Q charge is of the entire conductor. So this means that capacitor is capable of storing Q charge. But we know that total charge is 0. One conductor is at plus Q, one conductor is at minus Q. So if we consider the total net charge on the capacitor is 0. But in problems and in derivations, we will not say that we will not consider total charge. We will consider how much charge capacitor can store, and it can store plus Q charge. Okay. So this is the diagrammatic representation. One conductor will be having plus Q charge. Other conductor will be having minus Q charge. This conductor is at V1 potential. This conductor will be at V2 potential, such that the potential difference between them is V1 minus V2. V1 is at higher potential due to positive charge, and V2 as at lower potential due to negative charge. Okay, this is conductor 1, this is conductor 2, and the medium between these two conductor is insulator. Figure 2.24. a system of two conductors separated by an insulator forms a capacitor. So two conductors that are separated by insulating material, one will be having plus Q charge, one will be having minus Q charge, and there is a potential difference between these conductors that is being produced by a battery terminals is called capacitor. If you have any doubts, you can ask. To understand the capacitant, capacitors and its properties. The electric field between the conductor is proportional to charge Q. Okay, so the electric field between the conductors. Now, one conductor is at positive charge, one conductor consists of negative charge. So, electric field will produced from positive to negative. So, electric field will produce from positive to negative. Okay, so the electric field between conductor is proportional to Q. So if the amount of charge on the conductor is more, electric field will be more, because electric field is proportional to charge. If charges are less, electric field produced will be less. So doubling the charge doubles the electric field. So if we double the charge on the conductor, electric field will also get doubled, following Coulomb's law and superposition principle. So if this electric field will be from positive to negative charge, from here to here. Okay, so if we increase this charge, if we double this charge, make this 2Q, make this charge minus 2Q, then electric field will also becomes 2E. It will become double. Okay. Gain figure 2.24. Okay, the potential difference V represent work done per unit positive charge moving a test charge from conductor 2 to 1 against the field. V is proportional to Q. Now, there is electric field present between two conductors. Then, now, we have to move one positive charge, unit positive charge against this field. Against this field means from negative conductor to conductor at positive charge against the electric field. So we have to move this unit positive charge against this electric field. So how much work we have to do is stored in the form of potential energy, but we are using here unit positive charge, so this will represent potential. Okay, so what is the potential difference between these if these are 2 point charges, 2 points, 1 point and this is second point. So we have to move a charge from this point to this point against electric field. So we have to do some work, and this is the potential difference. If we are using unit positive charge, then it is the definition of potential. So potential difference between these two positive charge will be proportional to electric field. So if electric field is strong in that region, we have to do more work to move that charge against the field. And field is proportional to charge. If charge is more, field is more. Okay, these three things are interrelated. If work done to move a charge is more, that means electric field present in that region is more. That means charge on the conductor is more. So hence, this potential difference is proportional to electric field and proportional to Q. So what amount of charges are present on the conductors? Potential difference is proportional to this, or charges are proportional and vice versa, we can say. Charges that are inducing on these conductors will be proportional to potential difference applied across the capacitor. What amount of charges are induced on the two conductors of capacitor? It is dependent upon what amount of potential difference we are giving to these conductors with the help of battery or any source. Okay, so V is proportional to Q means V is equal to Q and some proportionality constant. So making ratio Q by V constant. So V is proportional to Q and this is the proportionality constant. And this proportionality constant C is known as capacitance of the capacitor. So this is the constant of proportionality and known as capacitance of the capacitor. That how much charges a capacitor can store for a given potential difference. Now this is constant. So it is not depending upon not on Q, not on V. Okay. So we cannot say that this is this C is dependent upon Q charge and V voltage. No, because this is constant appeared due to proportionality. Okay. So this C is not this C doesn't depend upon Q and V. It only depends upon geometrical configuration and dielectric properties. So what type of dielectric is there? C depends on that thing, and geometrical configuration. That what is the distance between these conductors? Okay, what is the area of these conductors? So this C is depends upon only geometrical configuration and dielectric properties. Doesn't depend upon the Q and V. Now, SI unit of capacitance is 1 farad, which is 1 coulomb per volt. Okay, 1 farad, charge upon volume. So 1 farad is 1 coulomb upon 1 volt. Okay, so this is the SI unit of capacitance, 1 farad. Fixed capacitance is shown by this sign. This is similar to battery, but in battery one terminal is shown by long line and one is smaller line. The capacitor symbol is 2 lines of equal length. Okay, so this is the symbol of capacitor, fixed capacitance, and variable capacitance is represented by this symbol. Okay, variable capacitance means we can change the distance between the conductors, or we can change something that will change eventually the capacitance of the capacitor. So it is that capacitor is known as variable capacitor and having variable capacitance. Large capacitance allows storing large charges Q at relatively small potential difference, which is practically important. So what we want to store large amount of charges for small potential differences, because capacitance is Q by V, means capacitance is equal to charge upon volume, voltage, potential difference. So if the capacitance is large, which means Q by V, ratio Q by V is large, which means large amount of charges are being stored at relatively small potential difference, which is practically important. We want this thing, small potential difference. Why small potential difference? High potential difference creates strong electric field that can ionize surrounding air. So if the potential difference is more, then large amount of electric field will produce strong electric field. Large amount of electric field causes what? Ionize the surrounding air. It will break down the molecules of the air into ions, and these ions, positive ions will combine with the negative charges on the negative conductor, and negative ions will combine with the positive conductor. This will neutralize the conductor and hence reduces the charge storage. Okay, so this is not required here. So dielectric strength is about 3 into 10 to the power 6 volt per meter. So dielectric strength of air is about 3 into 10 to the power 6 volt per meter, corresponding to potential difference 3 into 10 to the power 4 volt for 1 centimeter conductor separation. So this is the amount of electric field that will ionize the air. So this is the high amount of potential difference and we don't want it. For storing large charges without leakage, high capacitance is necessary to keep the potential difference below breakdown limits. So we want high capacitance so that it can store large charges at relatively low potential difference below breakdown limits. 1 farad is typically large unit. So we use 1 microfarad, 1 nanofarad and 1 picofarad. These units will be used in the upcoming lecture. Okay. So 1 farad is very large unit. We will rarely use it. Capacitors are essentially components in AC circuits as detailed in chapter 7. So in chapter 7 AC currents, we will also use these capacitors widely. Okay. So thank you. I hope you enjoyed the session.